are delayed by 3 minutes, more than 3 minutes, I will not give you that minutes. Yes? Correct. So you have some thickness D, right? And you asked to find the potential inside and outside, and also from the electric field, whatever we have calculated. So the inside electric field, right? We have E is equal to rho. What was the equation for this one?
D by 2 epsilon.
D by 2?
Epsilon. That's all.
This is outside, right? Inside will be depending upon the
Rho D L by epsilon.
So this is outside. Okay? And inside, rho Z over
Epsilon.
epsilon. And you asked to find the potential. So you have this infinitely low in X and Y, right? And for example, this is so this we have discussed in the last class. So you already know how to find the electric field. So we will just take it more. So that you can imagine. Okay. So this is your thickness. This is your thickness. And you have going to point Z. So this is infinity. This is infinity. This is infinity. Let's say this is 0. Right? And XY planes are infinity. And you only have the electric field on the Z axis. That's why when you are taking the electric field inside, it depends on the Z. But you have the flat surface, which is infinitely low. And when you have the charges here, right, the electric field outside will be a constant, right? Depending upon the distance where we are taking. So if the thickness is D, it should be rho D over 2 epsilon, where rho is the volume charge density. And now, let's see how the potential can be calculated. So this is something like what is potential as a function of this, right? So as I said in the last class, for line of charges from infinity to infinity, right? Minus infinity. If you are taking a reference 0, typically we say this is minus infinity. Otherwise, you know, if we don't have a reference, we just say that infinite. So in that case, we assume that the question was to find the potential at this point, V of R, right? And you assume that at arbitrary point, which could be very far, which is not an infinity. At infinity you have V infinity, you have charges, so you don't have the potential 0, right? So you assume some point R here or wherever it is, and you assume that it is 0. This is purely an assumption. There is no real world example I can show you for this kind of problems, okay? So, for any kind of problem related to the infinity, you have to assume a point where the potential is 0. That's the key point of solving this problem. So, if it doesn't matter whether it's a slab or if it is a sheet of charges or if it is infinitely long disk or if it is infinitely long cylinder or infinitely long wire. So, you have to take a point where the potential is 0. So, for the infinitely long wire, we randomly choose a point R where the potential is 0. But in this case, if you look at the electric field for this particular problem, for example, I have Z is a function of electric field, right? Let's say I have Z, the field is, let's say the thickness is over. For the Z axis, I have something like E by 2 here, E by 2 here. And this separation is the thickness is something like D, right? So, what is the electric field at the inside at Z is equal to 0? Z is equal to 0. Ez is equal to 0 at Z equal to 0 because you have rho Z epsilon 0 is the electric field equation, so it will be 0. And it goes linearly, right, up to d by t, right? Then it goes as a constant. So here it will be rho z by epsilon 0, and here you have rho d by 2 epsilon 0, right? You similarly have the charges in this side, so the potential will be, so the electric field will be going this way and this way. So minus rho z over epsilon 0, and this one is rho d 2 epsilon 0. It's clear? So where should we take the potential 0 in this kind of? We typically take at 0, even though it is not 0. Because when you have electric field 0, you should have a constant potential, right? Ideally, that's the correct way of looking into it. But to simplify the problem, we just assume that at z is equal to 0, I assume my potential V of z is equal to 0 is 0. This is purely an assumption. So this is applicable to all these kind of problem when you have some thickness, a volume charge distribution of a slab, or volume charge distribution of a cylinder, or if you have a volume charge distribution of a cube, or wherever the symmetry is there, and wherever the volume charge distribution is there, at the center, you will have, of course, you will have at z equal to 0, the electric field will be 0, or all of this symmetry. And for our convenience, we assume that at z is equal to 0, my potential is 0. In reality, it is not the case, okay? So, from this chapter, the thing is that the most difficult part is that you have to identify the symmetry, and you have to identify which kind of potential you have to choose, or which, for a certain problem, where you have to take the potential 0, right? When you have a sphere, I told you, you have to take the infinity, is potential 0, right? When you have a line of charges, you arbitrarily choose a point R where the potential is 0. For a slab of charges, you have to choose at Z, the potential is 0. So you have three kind of reference point for the potential is 0, okay? And if it is an infinitely long sheet, you assume at Z is equal to 0, you have the potential 0. So whenever there is an infinitely long thing, you have to make an assumption that somewhere the potential is 0, and whenever you have a volume charge distribution like a slab, or a long cylinder, infinitely long cylinder, and all these things, you choose the center wherever the electric field is 0, the same point where the potential is 0. Correct? So this is purely an assumption. I cannot give you any other logic for this assumption. Okay? This is how you have to solve this problem. If you look at the physics perspective of this one, in physics, when we calculate the potential, we don't calculate the potential at certain point. We calculate the potential with the reference to any point. So we typically take the potential differences, right? But for your course, the potential difference we take, always we have to have a 0 potential. With respect to that, we have to take the actual potential, right? So in reality, in physics, we don't care whether my reference potential is 0 or my reference potential is of having a 10 volt or some number. I only take the potential difference between them. But in your case, you have to assign a potential 0 at any point for all the problems, right? So for you have a sphere or point charge, at infinity it is obviously 0, you don't have a charge, right? Because V is going proportional to 1 over R. But when you have a line of charges, at infinity you should have a potential so that you cannot take the potential 0 at infinity, right? So you choose an arbitrary point. When it comes to slab of charges, you assume that at the center of the slab, Z is equal to 0, you have the potential 0. This is clear? So when you solve the problem, you have to identify which is a symmetry there, whether it is a surface charge, whether it is a volume charge, and you have to assign the potential reference 0 accordingly, okay? So this is purely an assumption, so yeah.
Does it matter if we take it as a 0?
It simplifies the problem.
But in the end, we can take
The problem is that when
any
you
point, right?
when you take any point, you the problem, for example, line of charge side particularly mentioned you have to make it at 0. You can take at any point, but when you do the integration, you will see another term which comes from there, the reference point is, right? So when you do the integration from 0 to something, the 0 term will be you will have the 0 point, what is the starting point, right? That will be 0. But when you have some value there, and you are integrating from there to here, you will have the integral value something there. So that's why we need to choose potential. Any question? Yeah.
So it's just for convenience?
This is just for convenience. For your course, it's just for convenience. But in reality, there is a lot of things when we do the approximation method to solve the potential. It makes sense when you learn little advanced physics, but for now, it's just the pure convenience. Okay?
This still applies for sheets as well, right?
This still applies for the sheet as well. Okay. So now, what is the potential inside? I have the potential, right? For delta V, I'll write all this stuff.
V
V
F
final
minus V
or
R.
minus V initial should be equal to minus of initial to final E dot D, right? This is very important for the quiz. So, V final is the point where I want to take the inside potential. For example, V final will be any point inside on Z axis, right? Minus, I take my Z is equal to 0 as the initial point I start, okay? Which should be minus 0 to the point I want to take the potential, easy, good, easy, because dz I choose because my potential is on Z axis. So my dl, whatever the integral, line integral or the one dimensional, I choose the Z axis as the integral, changing the values, okay? So this is, I assume that this is 0. This is purely an assumption, that's why I don't write this is equal to. So this will give you V of Z at any point inside will be minus of 0 to Z. And what is the electric field inside? Rho C over epsilon 0 dz, right? So when you integrate this one, you can take rho over epsilon 0 outside, integrate of 0 to Z dz, right? So what is integration of
This is
x
over.
dx of rho over epsilon 0 z square over 2 0 z. So you will get potential inside is equal to minus rho z square over 2 epsilon 0.
Professor, that's the slab question, right?
Sorry?
That's the slab question.
This is the slab question.
When we solved it to find the E inside,
Yeah.
we denoted the height as 2A. So instead of having 0 to Z, I wrote it from 0 as in the middle, all the way to G over 2.
Yeah, sure.
Half the distance
Sure.
there. So I got D squared over 8.
Yeah,
That's
sure.
fine.
That should be fine. So if you want to apply, his question was that if you want to find the potential from 0 to at exactly at D half, right? So instead of Z, he has to apply the limit is D half. That I will be coming to for the next part of this. But this is the any point inside you take this position. Whether it is a D by 4 or D by 8, whatever inside, just after the point from 0, you can find this value. So supply the Z value. Yeah.
A question regarding a sphere of charge. Is there a difference how we find the V outside or inside? It's the same thing, or is there a different?
There is a difference between E inside and outside. This is purely E inside. Sorry, V inside, right? So for the slab of
For the slab.
charge, yesterday I did the cylinder, how you do the Gauss's law and stuff like that.
Cylinder, yeah,
Did
but
that.
for the sphere.
B inside 0, sir.
For the sphere, if it is a hollow sphere, it's a constant inside.
Q and C 0.
So electric field doesn't change.
بالعكس.
So sorry,
Yes,
electric field, hollow sphere, electric field is 0. So potential doesn't
مو
change.
نفس اللي تو رابط.
So if you give us a question, it will be always outside.
Equal to 0.
Typically outside.
No,
So this is inside, right? Let's look at outside. How you solve the potential outside?
Understand it now.
So now, for the potential outside, from where to where I have to integrate? Delta V over? That is just on the surface. If I want to go further, on the Z axis, delta V is equal to V. Let's assume any point on Z axis, outside. Okay? Minus V Z is equal to 0 at initial position. Excuse me. From the reference point 0 to any point on Z axis. For example, for the inside we saw that if I have the thickness of sheet B, so this is B by 2, half of this one, this is B by 2, right? So if I am going from 0 to B by 2, I have rho Z square over 2 epsilon 0. This is the potential. This is inside. Now I want to check what is outside all the way, any point on Z axis. Okay, that's what I'm going to do. So that's the difference between this Z and whatever the Z I have mentioned. So this will be equal to 0 to Z E dot dl. Right? But what kind of electric field I have to choose for this one? I wanted to go from all the way from a 0 point to any point outside, right? So I have to include whatever the inside potential also, right? So my reference point is 0, which means I will have some potential until d by 2, which is affecting due to the inside electric field, and then from d by 2 to any point on Z, which is due to the outside, right? So I can split this one, this integral, and this I assume this is 0. So B of Z at outside can be split into integral of 0 to d by 2. This is inside, right? E dot dz plus d by 2 to z E dot dz. You got this idea? So you have this slab, right? You have this slab of thickness of D. So the first part we did just solve from 0 to wherever this D by 2 is, right? Now we want to find what is the potential outside. So if you are taking 0 reference, you have to include this inside one plus the outside one, right? For the outside. So if you do that integral, you can quickly do that. Or you want to do that integral yourself? Yeah, it will be exactly whatever I have done. And the limit should be, instead of Z, I should be having the limit divided. So this will be, I'll quickly do this. So I can take 0 to d by 2, right? Ez will be rho Z over epsilon 0, right? dz minus, I took the minus outside, so minus minus. So this will be rho d by 2 epsilon 0 into dz, right? So this will be rho Z square, sorry, if you do this one d square by 4 epsilon 0 minus, okay? This one will be this d by 2. So this will be, so I like this will be square. So integral d by 2 to Z, so Z, so dz, right? So this will be, so this will be minus rho d square 4 epsilon 0 minus rho d 2 epsilon 0 into Z, right? Minus minus will be plus rho d square 4 epsilon, right?
Professor.
So this will be
معلم جاب بي منين؟ ها؟ جاب منين بي دي سكوير؟
Did you say P?
you have already one d, right? So this will be equal to, so what is, if you add these two, so that will be d by plus d by 8, right? So that will be rho over 2, sorry, rho over d square 8 epsilon 0, right? Minus of rho d over 2 epsilon. So this is the potential outside. This is minus, right? Minus d. So this is how you will get the potential. So when you plot this one, how the potential look like? You have potential here and z axis here. All the potential, whatever that E inside, which is going minus z square, right? And you have a constant term on this potential. So this will be going linearly. So this is how your potential will be. So this will be rho d square over 8 epsilon 0. So how many of you solved this way?
There is one like
How many of you got this answer?
like this and go like this.
You got it?
Yeah, but PD out there.
Well, I can just
Now it's like here and stuff.
Let's go to the next problem.
انا ما لحقتش حتى اصور.
Maybe you can try that solving this one. You just solve this integral.
Let's
Yourself. So the graph is just
صورته؟ لا لا هو
this
اسمع انت
inside
صورته؟
potential, whatever it is,
صورته؟
right? This is negative rho over
إيدي ما
epsilon
تشوف إيدي
zero.
شيء.
Sorry, here. Rho d square over epsilon zero, right? So you have z function here. And negative z square function will go like this. Right?
ماشي في البداية
Then you have a
ياكل 1
constant
3 بيز
term.
بي اوفر بي.
Yeah. And then
I go to 2.
we will do one more problem. So far we were going from electric field to the potential, right? Ahmed. So far we were going from electric field to potential, right? Now we will go from the potential to electric field. So if you want to go from potential to electric field, the electric field Ex will be minus dou V over dou X, right? Dy will be minus dou V over dou Y. Ez will be minus dou V over dou Z. Or generally, in 3-dimensional you can write this is negative gradient of potential. Right? So I have a question. This question we didn't do when we were doing the chapter 22, but I will ask you to do here. Dipole problem. You have a plus q charge here, okay, and a minus q charge here, okay, and this is x-axis, and these charges are set on y-axis. Let's say I fill the and I ask you to find the electric field and potential. Typically, I ask you to find on x-axis or something like that, right? So I ask you to find some f-axis potential, which is a distance of r. How do you find the potential? Due to a positive charge here and a negative charge here. Since it is a dipole, we can assume that they are separated by a distance of d. So this will be b by 2, and this will be yeah.
So Professor, we already have the formula for the dipole. So you just take
If we have the formula for dipole when you have a point on x-axis or when you have a point on y-axis, I don't remember which symmetry you have, but we didn't have a off axis. So, Ilyas,
you should integrate it.
I'll be asking this kind of question in exam, and you should not complain that you didn't discuss in the classroom.
Of course.
If you are not
Someone take a
listening,
picture.
if you are not listening, there are two ways. I can kick you out of the class, or I can fail you for the exam. Whichever you want, you can choose.
Okay, so Professor, can
Yeah.
we just integrate that formula and then derive it with respect to x, y, and z to get the...
So first you have to find the potential,
Yeah, exactly.
right?
Yeah.
So how do you find the potential? So you have this point, right, from this center. So the potential you have to take for a particular charge with reference to that charge. If you are taking that. In your textbook, you must have seen this one is represented as R plus because I am taking the reference point with respect to the positive charge. And I have R minus with respect to negative charge. Okay? It's clear? So to find the potential, what would I need? Q over 4 pi epsilon 0 R, right? So if I want to find the total potential of this system, which is on x and y axis, I have to find the potential of the positive charge plus potential of the negative charge, right? So what is the potential of the positive charge? 1 by 4 pi epsilon 0 Q by R plus, or you just write Q over 4 pi epsilon 0 R plus. And what is V minus? It's a negative charge, right? Q over 4 pi epsilon 0 R minus, right? Now, what is my total potential? Q over 4 pi epsilon 0 1 over R plus, I just take the common terms, minus 1 over R minus. So if you find the R plus and R minus, you can solve it. Right? So how do you find R plus and R minus? So what is this distance? Divide. Let's say this, I have, this point is on the y-axis side of y. Okay? So what is this distance?
Y by 2. 1 minus divided
From here to here. Y minus
to d over 2.
dy 2, right? And what about this one?
Root of 1 minus divided 2 squared plus divided 2 squared.
Y plus D
Y plus
D over 2.
y plus d over 2. Okay? So now we have a rectangle, right? Right? So this is 90 degree here, right? And with respect to this is 90 degree, right? I will remove this equation. Anyway, we have the equation there, so this one will be this is a 90 degree. Right? And this is the angle 15. So you can write the R in terms of R is the hypotenuse, right? So R in terms of the adjacent side, square root of the adjacent side, square root plus the opposite side, right? Like this. So R plus can be written square root of x squared. Let's assume that this is on x-axis. For example, I'll be giving all these quantities. X squared plus what is my y? Y minus d by 2 squared. Can I write this R plus this point, this squared plus this squared, square root, right? Square root of x squared plus y minus d by 2 squared, right? Similarly, this R minus square root of x squared plus y plus d by 2 squared. X squared plus. Right? Now you can just expand this one and find the potential. Yeah. So how you find the electric field there? You can find the electric field, but then if I ask you the potential, you can find the potential. But this way it is easy. Because this will be for the electric field. If you want to find the electric field directly, you have to have the R plus square. So it gets complicated. Yeah, so you have to assume that this is the easiest. And then, for example, you just assume several things here. R is much greater than b by 2 and all these things. And you expand this one. You want me to do that, or can you do this?
We can do it.
You can do it?
Don't worry.
So R plus
Yes, man.
R plus is equal to x squared. What is 1 minus epsilon over n when I have the epsilon much less than 1? Binomial expansion. We did it several times.
1 minus en.
1 minus n epsilon. Right? So this can be written in terms of epsilon. Right? And you can solve it. Or the other way is that you can just expand it and just y squared minus 2 d over 2 into y and plus y squared into this. You want me to solve this?
You can.
Sorry? No, the binomial expansion is in this one, in the first step, whenever we are considering the epsilon is very less than 1, because I have the assumption that d by 2 is much smaller compared to the r distance.
So the value in epsilon you provided?
The epsilon is here is whatever, when you have, do some rearrangement, you can just,
So we absolutely know how to do it.
you should know. I skipped several steps here, by the way. You want to follow those steps and just
Yes.
reach us up to here?
Yeah.
Let's see first this part. I'll ask you to do the R minus. That should be a reasonable things to do. So let's find x squared plus, I expand this one, y squared minus 2 into d by 2 y, right? So what will be this? Minus y d, right? Plus b squared over 4, right? And what is x squared plus y squared here? I have x squared, whatever is y squared is my r, right? So r plus I can write in terms of r squared minus y plus b squared over. R is the distance from the center. The first R I have defined the point from the center. And R plus is the distance from the positive charge. R minus is the distance from the negative charge. Right?
How do you do that?
This one.
Square plus y square.
So I have R is square root of x squared plus y squared, right? Right? So R squared equal to x squared plus y squared. So I just take this whole part.
Also the big, original.
The original R. So now I take the R outside, right? And y b over r squared plus b squared over 4 r squared. If I take r outside. You can do in a different, many other methods. But this is easiest way. I will explain step by step. Okay? So when I have an assumption, r is much greater than d, this, I neglect that term. And this term, I can write r 1 minus y d over r squared minus 1 by 2. Right? Now I apply this one.
Oh, yeah.
Because I took it from the square root. Right? If you are unable to follow, just write down the steps. I expect you have some calculus and some numerical math background. That's why I'm not explaining everything. But if you are having difficulties for just copy this.
Is it possible to do this without binomial expansion?
You have to assume that if you do without binomial expansion, you will have this quadrupole. Right? So for a dipole, we should have that only dipole. So you assume that further terms for the dipole, you will just neglect it, and especially the quadrupole. So remember, when you do the 4 charges together, you didn't get this term. Instead of you get this term, right? In the final answer. That is a quadrupole. So those terms will not be there for the dipole. That's right. That's what we are using the binomial expansion.
Professor, why is it minus half, the power minus half?
This one?
Yes.
So if this is my square root, right? Sorry, this is not minus. So this is the square root. Right? Thanks for that. So now I have this one. This will be 1 over LH, right? So similarly, if I have this one, 1 minus yd over r square root, I can write 1 minus, right, half y d r square, right? Like 1 plus epsilon power n is 1 plus whatever the power is here, that should be here, right? Into the term whatever the epsilon here. So this is an epsilon, correct? Can we set that? Right? So now you just do this one. I mean, you have to do this couple of times. So r plus will be equal to r into 1 minus half yd over r square, right? And what is 1 over r plus? We actually want 1 over r plus here, right? So what is 1 over r plus? 1 over r, 1 minus r into y d over r square. Sorry, no square root. So this is it. So next time you take this one, 1 over r, whatever this one, you take it outside. So that will be 1 minus half yd over r square minus. Now you expand this by using 1 over 1 plus epsilon power n. And you solve. Right? So 2 times you have to do the binomial expansion.
So for r minus, it's just different sign?
So r minus, you just switch the sign. You have to try the do the r minus. Right? Because if I doing this one on the board, it will take more than half an hour. Because I have to go for the r minus, but I will tell you how to do it. Okay? So that you can practice it. And I can provide a solution for this one. Then once you have this one, 1 over r plus like this, right? And you will get 1 over r minus, just switch the side. Then you can write the potential in terms of r. That's the whole idea. Sorry, this one is minus half, right? This one is minus half. Because I have, this is not a square root, this is minus half. You want me to do this for both steps or just I'll do for the 1 over r plus. 1 over r plus is equal to, if I use the binomial expansion here, 1 over r into this one will be, this whole term will be, if I assume like this, 1 plus half yd over r square, because minus 1 minus will be plus, right? So this will be 1 plus half y d over r square. This is my 1 over r plus. Similarly, if you do 1 over r minus, you will get 1 minus half y d over r square over r. So you can write the total potential V plus minus, sorry, V plus V minus will be Q over 4 pi epsilon 0, 1 over r plus minus 1 over r minus will be equal to. Okay, I'll do for the electric field. You can do the potential. I will just tell you how to differentiate. to find the electric field from the potential. So this will be V is equal to Q over 4 pi epsilon 0, right? I take this R out, so I can have R here, then 1 plus half Y D over R squared minus of 1 minus half Y D over R squared. Okay? So this one cancels, and minus minus will be into plus. So this will be Q over 4 pi epsilon 0. R half will be 1, so that will be YD over R squared. So you will get a potential Q over 4 pi epsilon 0, right? YD over R cubed. Right? And now, this is a two-dimensional problem, right? So you have an electric field on x-axis and y-axis, right? So you have two components. So this R you can write back in terms of x and y. So this will be V is equal to Q Y D over 4 pi epsilon 0 into x squared plus y squared over 3. Right? I just wrote instead of R cube. So R is square root of x squared plus y squared, right? So R cube will be 3 times of that. So 3 half. If you didn't follow this one, take a picture and practice yourself and just ask me later. Okay?
Professor, so you know how V is equal to negative KQ over R?
This one.
Yeah, so it's KQ over R.
Yeah,
right?
yeah.
But it has a negative sign.
Yeah.
So then, if you want to have V plus V minus,
Yeah.
the positive will go to the other side.
Yeah.
Okay, so isn't this supposed to be 1 over R minus 1 over R plus?
No. It is just that the potential, when you represent the potential, it doesn't have any direction, right? When you represent the potential for a negative charge, you always represent with the whatever the charge value. So it's a magnitude, right? So you just represent that minus Q over 4 pi epsilon. I think I have deleted that part. So this minus comes from the minus Q over 4 pi epsilon 0. So the V minus is minus Q 4 pi epsilon 0 R minus. R minus is the distance from this minus Q to this pole.
The equation is V is equal to Q over 4 pi epsilon, and then 1 over R plus minus 1 over R minus.
Yeah.
And then if you go up, you added an R in the denominator.
In here.
Yeah.
So I just 1 over R plus is, so I skip one step here. So V is equal to Q over 4 pi epsilon 0, right? This will be 1 plus half YD over R squared minus of R minus of 1 minus half YD over R squared over R, right? So I took this R outside, so I have that here, right? So yeah. So you have to practice yourself, then only you will understand this. This can have a lot of mistakes. Like when I was writing this one, I did a mistake here. Instead of minus 1, I just put my half, right? So when you look back, then you will understand. So if you didn't understand it, just take a picture. This is very, very important question. I can change the position of this one, the whole word. You can just find it. I can keep it here, or I can keep a negative charge here, a positive charge here. So those kind of questions will come in exam. Okay? So you have to practice it. The thing is that when you look this one, you have a lot of steps because I wrote each and every steps. You don't need to write all these steps. You can skip from here. You already know this expansion here, right? So you can skip to this step. directly if you want. And from here, you can skip. From here, you are trying this one, the binomial expansion. From there, you can directly come here. You don't need to write this. So I have written all the steps so to make you understand. And now, this is the potential. Now, how I find the electric field from this one? So I have a two-dimensional problem, right? So I'll have the electric field will be Ex I cap plus Ey j cap, right? So Ex will be minus rho v over rho x, right? So this will be minus rho into q y d over 4 pi epsilon 0 x square plus y square 3 by 2. And you take the derivative with respect to x, you will get this one. So this you have. I did all other steps, right? So you can do this. And what about the y component of the electric field? So y component will be minus rho over rho y of q y b over 4 pi epsilon 0 x square plus y square 3 by 2. I can give you hints how to take the differentiation. So this differentiation is much easier because you can take q, y, d are not dependent upon x-axis because we are taking the partial derivative, right? So this is a constant, this is a constant, y is a constant. So if you take a differentiation, you can take 3 by 2 to up and minus 3 by 2 and just do this one, right? So this can be quickly, this will be q, y, d over 4 pi epsilon 0 into minus 3 by 2 into 2x into x square plus y square 5 by 2 minus 5 by 2. So this will be q, y, d. I'm not writing all the steps, 4 pi epsilon 0. 2 will be cancelled. So you will have, so minus, here there is a minus will be cancelled. So that will be 3qyd into x, right? Divided by x squared plus y squared over 5. This is for the ex part. And for the ey part, you have to have some knowledge about the differentiation for two functions. You have here with respect to y, right? So you know how to differentiate if you have two functions coming together. So this will be first function and take the second function differentiation minus the second function, take the first function differentiation, right? So you have to know that. And this is understandable for the next class. And I have other problems too, but I will be quickly showing the problem on the screen. You can copy this problem. This problem is very important. This can come for the exam. So don't blame me later. I didn't mention it.
I understood the syllabus so far.
انا داش ريكوردينج كلاس ما داش ايدي عورتني.
See, the problem is that when you make noise there, I cannot focus the same time on the board and same time on you. I cannot point out, it's not a high school or this thing like that, right? I cannot point and go, shut up, silent. It's not good. So when I'm solving a problem, if I wanted to make you clearly understand, keep silence, okay? Then I will be, otherwise I'll just switching from one step to other step, I'll be going quicker. Because I have to finish the topic also. It's not only about just covering, teaching you every steps and all these things. It's also about completing the course, right? So, if you keep silence, I'll just explain in very detail by taking time. But if you make noise and all these things, I have to give attention there, so we will be losing time. So we are limited with the time, okay? And this is the problem I give you as a class activity for this chapter. Last chapter we didn't give anything, but from this, take a picture of this one. So this problem I can just briefly explain. if you want me to explain. So this is also going from potential to the electric field. So this is an annulus, which means a cut disc. So this is having inner radius this one and outer radius this one, and ask you to find the potential at a point on z-axis, right? So to solve this one, for the electric field for a disc, you remember you solve this. Assume that a small ring, right? It's like the onion ring, right? And you just take a point and just solve it. Similarly, when you look at this one on a side view for this ring, you can just find this on the z-axis, and you have to find this distance and just find dv. So due to this dq, you have to find dv, right? So and you have to integrate over this one. Then you do. 1 minute solve it. So everything should be easy, right? If I solve it. So you try this one. I'll give you the solution. But write it down and just try this one and submit it. I'm seriously looking into the class activities. Don't blame me at the end of the semester, we didn't get this grade and that grade. If you are not actively doing these problems, you will get the grade for sure.
Okay, so Professor, how about you let us go early? Give us this and the
Sorry?
Give us this and the class activity and let us go early. You can have some energy to solve the question.
You will get energy by looking at your midterm answer sheet. When you see the midterm answer sheet, it's kind of problem. Right?